Okay. The question is, every day, the number of messages, email messages that I get is a Poisson random variable with mean 10, independently from day to day. Okay? In a total of 10 days, find the mean and variance of the number of messages that I get. Okay? What do you think? Let R be the number of messages in 10 days. Okay? So I can express R as the sum of L sub i's, I from 1 to 10, right? And Li is the number of messages on day I. First of all, what is the expectation of R? R is the sum of Li's. So whether or not Li's are independent, the expectation is always the sum of the expectations of the Li's. Okay? What is the expected value of Li? It is given in the problem to be 10. Okay? Is it 10? Yes. Okay, now I read the problem again. It's the number of messages in 1 week, not 10 days. Okay, correction here. Excuse me? Excuse me? Yes. Thanks for letting me know after I noticed it myself. Okay. So now, what is this expectation? 70. Okay. That's easy, whether or not Li's are independent. Okay? So now what is the variance of R? Variance of R, we just proved. Excuse me? What? The variance of R, we just proved, is equal to the sum of the variances. Sum of the variances of the Li's, which is, well, the variances of Li's. Do you remember something about the Poisson? What do you remember about the Poisson distribution? Its PMF looks a little difficult to approach, but its expectation is very simple. It's equal to lambda. Its variance is also equal to lambda. Okay? So it has very neat properties. The variance is equal to, again, 10. So the sum of the variances is 70. Okay? Any question about this? So there's a lot of variance in this total number of email messages. Incidentally, here's something I would like to do as an exercise of independence and in exercise of conditional PMFs, which you will officially visit, we will officially visit later on in this class. But I'll do it now as an exercise, as I said, of conditional expectation, or I'm sorry, conditional probabilities. I would like to know the probability that L1 plus L2 equals K. What is L1? L1 is the number of messages that I receive on day 1. And L2 is the number of email messages that I receive on day 2. Okay? What is the probability that L1 plus L2 is equal to K? How can we do this? We know the marginal PMFs of L1 and L2. We can write this probability maybe using the total probability theorem. Let me start and I'll let you finish. I can write this as the probability that L1 is equal to M, okay, times the probability that L2 is, when L1 is M, for the sum to be equal to K, L2 has to be K minus M. Given, right, given that L1 is equal to M. What is the range for M? For the sum to be K, suppose K is a positive integer. K is a positive integer. So M can go from 0 to K, right? Why? Because the sum is K, and L1 is part of the summation. It can go from 0 to K. Okay? So now let's use independence, and I'm going to ask you to help me with this. Look at this expression, please. Because of independence, we can simplify this expression. By the way, while you're thinking, let's write these in terms of marginal and conditional PMFs. M from 0 to K, the probability that L1 is equal to M. What is this? This is PL1 of M, the marginal PMF of the random variable L1, evaluated at M. This is what? This is the conditional PMF of L2 conditioned on L1. Okay? Evaluated at K minus M. Okay? Any problem up to this? Go ahead, please.
Bu iki gösterim arasında ne fark var? Yani bir L1'ı L2'yu aşağıya yazıp oraya
Because we just defined this thing PMF, probability mass function. It's just a notation. You're right. It's just a notation. The probability that the random variable x equals x is denoted as px of x. If you want, it's a shorthand notation. It's debatable whether it's shorter or not, but it's just a notation that's standard in probability theory, so we're using it. Right? Okay. Later on, actually, in fact, as of next class, next hour, when we do when we look at continuous random variables, there will be a continuous version for this function, the probability density function. In that case, that notation will really be useful. Okay? Okay, now let's see. Can we maybe simplify this? Because, very nice. L1 and L2 are independent. So, very nice. Let me write this in red. Let me find my red marker. This is equal to the marginal of L2 at K minus 1. I'm sorry, K minus M. Because L2 is independent of L1. So the conditioning on L1 just disappears. Okay, let me rephrase. Because L2 and L1 are independent, the conditioning drops off. The information given on L1 is irrelevant for L2. Okay? As we proved last time, let me rewrite here. If x and y are independent, this implies that the probability of x given y, meaning the conditional PMF of x given y is equal to the Px of x, the marginal PMF. Okay. So now, what do we have? We can now write this in terms of everything that we know. This is PL1 of m, PL2 of k minus m. Do we already know these marginals? L1 is the number of emails that I get on day 1. And L2 is the number of emails that I get on day 2. They are given to be Poisson distributed with mean 10. And we know the Poisson PMF. So all we have to do is substitute in the Poisson PMF. So m going from 0 to k. What is the probability that L1 equals m? Lambda to the m. What is lambda? Lambda is 10, right? 10 to the m. E to the minus. Maybe let's leave this as lambda for now. Okay, just to reach a general conclusion. Lambda to the m, e to the minus lambda over m factorial multiplied by lambda to the k minus m, e to the minus lambda over k minus m factorial. There's a surprise coming up. Let's see if we can notice this all together. Let me rewrite that probability here. The probability, well, let L1 plus L2 be R2. Okay, this is the total number of emails. Maybe, yeah, R2 here, like this. R2 is the total number of messages in 2 days. I know that R2 is the sum of 2 independent Poisson random variables. Okay? I just found that the probability that R2 equals k is given by the summation, m from 0 to k, lambda to the m, e to the minus lambda over m factorial times lambda to the k minus m, e to the minus lambda over k minus m factorial. Do you have any ideas for simplifying this expression? The lambdas can be combined. The lambda to the power terms can be combined, right? What else? Maybe let's bring lambda to the m times lambda to the k minus m as lambda to the k outside of the summation. E to the minus lambda terms become e to the minus 2 lambda and go out. And inside the summation, we have 1 over m factorial k minus m factorial. Does this seem familiar from somewhere? Remember your m choose k. And choose k. Remember k choose m, huh? K choose m would be k factorial divided by m factorial k minus m factorial. So how about I multiplied and divided by k factorial? And put a k factorial here. And the inner summation goes from 0 to k. Okay, I just multiplied and divided by k factorial. Here inside the summation, I have k choose m. Okay? K choose m, what do you know about k choose m? Very nice. If you sum k choose m, as m goes from 0 to k, you find 2 to the power k. Why? Because k choose m is the number of subsets of size m of a set with k elements. Okay? So if you sum this for all m from 0 to k, you are finding the total number of subsets of a set with k elements, which already we know to be 2 to the k. Okay? In other words, this is the binomial sum. Okay? This is 2 to the k. So let's see where that brings us. We have 2 lambda to the k e to the minus 2 lambda divided by k factorial. And that is the PMF of R2 at k. What do you see here? What do you notice about R2? Very nice. R2 is Poisson, and its mean is 2 lambda. So what did we just find? We just proved that when you add 2 Poisson random variables with the same mean, you get another Poisson random variable with twice the mean. Okay? That property is so useful that in a lot of advanced fields in electrical engineering, there are a lot of applications for this. Okay? An example is Poisson point processes, which is used a lot in tracking problems and estimation, biomedical signal processing, for example. Okay. Okay, so let's recap. What did we do? The number of messages I get, number of email messages I get every day was Poisson with a given mean. I computed the mean and variance of the total number of messages I get in a week. Okay, I used the fact that the number of messages in each day is independent of every other day. Okay. I also incidentally, as an exercise of conditional PMFs, showed that when you add 2 independent Poisson random variables, you get another Poisson random variable. Okay? Any questions about the mechanics of all this? Okay. The next example is also very nice. Okay. It's about computing averages. Okay. So in the real life, this has a lot of application. In order to estimate a probability, you go and take a lot of samples of that process and compute a sample average. Okay? And you hope that if you take enough samples, the sample average somehow converges to the mean. Okay? Next example is about that. Okay, so an opinion poll is conducted to determine the average public opinion on an issue. Okay? It is modeled that a person randomly selected from the society will either vote in favor of that issue, will say yes with probability p, or will vote against that issue. In other words, vote no with probability 1 minus p, independently from person to person. Okay, that's a model. It may not be a good model, but this is the model. Okay? The goal of the survey is to estimate this probability p. Okay? To keep the cost of the poll at a minimum, we want to survey the smallest number of people such that the variance of our sample average is small. In fact, it's smaller than 10 to the minus 3. Okay? So let's see how we can use the knowledge we gained so far to solve this problem. Okay, so first of all, let's understand the parameters of the model a little bit more. So each person I, let's say, person I votes in favor of the issue with probability P, okay, and votes against the issue with probability 1 minus P. Okay, so the vote of person I is a what? Bernoulli random variable. Okay, by this point, you can notice a Bernoulli random variable when you see it. Okay, now what is our sample average? Our sample average, so we survey, okay, suppose we survey a total of n people. And we count the number of people who said yes. What is our sample average? The number of people who said yes divided by n. Okay, that's our estimate for P. Does that make sense? So our estimate, let's call it S. S is our estimate. Okay, is the number of people who are in favor of the issue divided by n. Okay, but that's cumbersome. I would like to somehow use random variables. Can you define a random variable for me? The number of people who are in favor of the issue. Okay? Exactly. That's nothing but the sum of xi's. I from 1 to n divided by n. Okay? Because xi reflects the opinion of person I. Xi is 1 or 0. The sum of xi is the total number of people who vote yes. Okay? Now, why is this sample average related to P? Why is this a good estimate of the probability P? Do you think? That's sort of indirect. I'm looking for a more direct answer. Excuse me? Right. So if you took the expectation of this whole thing, because S, our estimate, is a random variable, right? Our estimate is a random variable. Why? Because the xi's are random. Xi's are random, so S is random. I can talk about the expectation of S. Expectation of S is the expectation of 1 over n xi, I from 1 to n. And this is 1 over n times P, which is P. Okay, so that makes sense. At least the expectation of my estimate is equal to P. Okay, so I expect my estimate to be a good estimate of P. I don't know what a good estimate means at this stage. But the question is suggesting something. The question says, you know, your estimate has an expectation which is P, and that's okay, that's good. That shows, in fact, in estimation theory, this is called an unbiased estimator, because its expectation is equal to what it's trying to estimate. Now the question says, your estimator is good enough, your estimate is good enough if its variance is less than 10 to the minus 3. Okay? So let's compute the variance of our estimates. what is the variance of our estimates? Variance of S. Let's see if you remember how to do this. Variance of 1 over n times summation I from 1 to n xi. We know, okay, xi's are independent. Variance of the sum of xi's would be the sum of the variances. That we know. But what do we know about that 1 over n? What do we do about that? What do we do about this? So, goes out. Very nice. It comes out of the variance being squared. 1 over n squared times the variance of the sum of xi's. Remember, the variance of ax is a squared times the variance of x. So the variance of the sum is n times the variance of x1. So this is n over n squared times the variance of x1. What is the variance of x1? x1 is Bernoulli. Last hour we showed that the variance of a Bernoulli is p times 1 minus p. Remember, it makes a peak at 1/2. P times 1 minus p. Good. Now we have our variance. And our boss, whoever is paying us to do the survey, tells us that the variance should be less than 10 to the minus 3. But, there's a problem. We don't know p in the first place. We're doing the whole thing to estimate p. Okay. So what do we do? The question is giving us a hint. Hint. An upper bound on the variance of a Bernoulli random variable is 1 over 4. So whatever this variance is, it's not going to be above 1 over 4 times 1 over n. So this is less than or equal to, in the worst case, equal to 1 over 4n. Okay? And if 1 over 4n is below 10 to the minus 3, then our actual variance will be below 10 to the minus 3. Right? So 1 over 4n being below 10 to the minus 3 will suffice, will be sufficient, which means n is bigger than what? 250, right? 250. So basically this says, it's a very general result actually. If you're interviewing people on a yes or no issue, okay, and if you are asked to have your sample mean to have a variance less than 10 to the minus 3, you can achieve this by interviewing 250 people. Okay? You don't need to interview more than 250 people. Okay? For a variance. If you interview 250 people, you are guaranteed that your sample mean variance will be below 10 to the minus 3. Okay? So this is 1 over n. And this is less than or equal to 1 over 4. Okay. In fact, this may be, okay, there's a basic assumption here, which is important for this whole thing to hold. We assume that the xi's are independent. So if you, for example, if you chose a group of people who tend to have the same opinion, okay, your sample mean may not at all be close to the average of the whole population. So here the 250 people, if you're selecting from an actual population, should be chosen to sort of reflect the average opinion. So try to select people as diversely as possible, right? That's, you know, if we're moving from the assumptions of this example to a real life survey, that's something to be careful about. Now, this sample average will play a big role later on in this class when we talk about convergence, because, in fact, that's, I think, one of the most important reasons for studying probability theory. This sample average will converge to the actual mean P under some conditions. Okay? And we will make that precise later on in this class. Probabilistic convergence. Okay, any questions about this? So this brings the discussion of discrete random variables to a close for now. Okay, the next topic in this course will be a discussion of continuous random variables. After we discuss continuous random variables, we'll have a lot of techniques to solve more sophisticated problems. Of course, discrete random variables will still be a part of our interest in this course. But I think we've covered a lot of the basic ideas and basic models. The rest should be sort of the topping on the actual cake. So hopefully by studying for the midterm, you will really bring your knowledge up to date. And once we start continuous random variables, you'll be able to follow the topics quite easily. Okay, I'll see you next time.